In this video, we are going to continue kind of building that analogy between the discrete and the continuous random variables. And we previously defined the PDF of a continuous random variable. Now we need to define the CDF of a continuous random variable. And it's defined in a similar way. It gives the same type of probability. It's just the way we compute the probability, or the way we compute the CDF, is different, right? All those summations, right, are now going to be replaced with integrals, right? So let's go ahead and start the definition. So the cumulative distribution function, right, our CDF, so CDF, and we still use the same big F notation, so big F of x for a continuous random variable. So for a continuous random variable is defined for all x, right, in the set of real numbers by this this relationship. And in fact, it's an integral, and it's still, so our big F of x, it still gives us the probability that x is less than or equal to little x. But now remember, so this is an interval here. This is an interval. Before I finish the definition, let me just remind you. So let's say we have, in theory, a PDF that covers the entire real line like that, and for any real number x, if I want to find the probability that my random variable is less than or equal to that number, then remember, we're using area to represent our probabilities. So it would be everything to the left of this vertical line, right? Because less than or equal to x could be anything from this vertical line down to negative infinity. So the area that now will be represented by our CDF is this area, right? So in principle, our lower limit is negative infinity and our upper limit is x. But the thing is, right, so let's write that down. So our lower limit is negative infinity, upper limit is x. But what we need to do is, so we can't have our the variable that we're integrating with respect to, we can't have that variable be my upper limit. So as we do in the fundamental theorem of calculus, right, when we're defining those area functions, because that's exactly what this is, we switch to like a dummy variable or a placeholder variable, and I'm going to use little t here, dt, right? So this is the definition of the CDF, right? And again, so this, again, if we continue the analogy, what this integral represents, it represents the area of the region to the left of my number x under my PDF. So this is now the area to the left of my little x under the PDF, right? And what we're going to illustrate right now is, how do we go, how, if I give you the PDF, how do I find the CDF? But again, the reason I mentioned that analogy in Calc 2, Calc 1, Calc 2, where you do your area functions, that's exactly what this is. This is just a specific area to the left of a fixed number, right? All right, so let's do an example and see at least how to find this CDF, right? Because this is all we need. All we need is this definition. I mean, we know how to use it. And in this example, what we will do, we will find the PDF given the, we will be given the PDF and we'll be finding the CDF, and then we can use it to compute certain probabilities. So let's take a look at this example. Again, let's say x is a continuous random variable, and here is its PDF. And we're going to have 1/8 plus 3/8 x. And I don't know, I seem to like the interval 0 to 2. So I'm going to have x go from 0 to 2. And again, it's going to be 0 otherwise. All right. And so here's our sample space. Again, we can tell by looking at the function what the sample space is. So x can take on any real number between 0 and 2. But this function now, we're given the constant. So we didn't have to figure out what the constant is. In fact, we can recognize that this is a linear function, right? So we could actually sketch this. Here is 0, here is 2, and we know it's going to be 0 down here and 0 up here. Now, when x is equal to 0, so at the left end point of this interval, this function has a value of 1/8. So it starts basically somewhere up here. And then when x is equal to 2, it has a value of 6/8. So, not quite drawn to scale, but roughly here. And then it's a linear function, so we can just connect these two endpoints. And that is now our PDF, a nice continuous function. Well, technically piecewise continuous, because it has jump discontinuities here and jump discontinuities there. But this is the graph of little f of x, right? So now, what does the graph of, or what is the PDF going to look like? Well, the idea is, again, it's very, very similar to those area functions. I wouldn't even say similar, it's identical. So if I now pick an x value, any x value between 0 and 2, right? Let's say it's right here. And if I were to find the area from 0 up to x, right here, then that area is what our CDF should give us, right? So this area here is going to be what our big f of x will give us, right? So if we were to pick this value of x and plug it in, it would give us the area from 0 to here. If I plugged in a value of x really close to 2, it should give me the area, again, starting from the smallest possible value of x up to whatever x I plugged in, right? So again, this is really just an area function. So if you understood the concept of an area function back in calculus, this is exactly what we're working with now. It's just that this specific area function gives us cumulative probabilities up to and including a fixed value of x, right? So let's see what it looks like. Well, if we apply the definition, right? Again, let's write it down. So this function that we're going to find, right? Well, it's going to have certain properties. So for instance, if I were to pick a value of x that's less than 0, right? Then there is 0 probability here. There is 0 area here. So I could say that this function is going to be 0 whenever x is less than 0, because there is no area here, right? The only time we start to accumulate, right, or accumulate positive area is when I get between 0 and 2, right? So this is going to be a piece of my function, right? Now let's say what happens when x is between 0 and 2. Right, so when x, let's say strictly between 0 and 2, right? Then my CDF, that's where I have to use my area. So I'm not going to write down the negative infinity to 0. We know that that's equal to 0 based on this inequality. But once I go from 0 to x, right, then I'll do my integral. And then now remember, the PDF is this function, 1/8 plus 3/8 x. But I'm not going to have my integral with respect to x and have x as the upper limit. Conceptually, that doesn't make any sense, right? So that's why we switch and we write it as 1/8 plus 3/8 t. It doesn't have to be a t. It could be u. It could be s. It could be some other variable, some variable that's not our little x, and then we integrate with respect to that variable, right? So what we're going to come up with is not a specific number. We're coming up with a function, right? And that function is the area function. It will give us the probability whenever we plug in a value of x between 0 and 2, right? Now, this part of it is pretty routine, so let's integrate. So the integral of 1/8 with respect to t, that's 1/8 t. Then the integral of 3/8 t, that is 3/16 t squared. And then yeah, we're gonna integrate or evaluate it, from 0 to x. All right? And then, so when we plug in our upper limit, we switch back. So now we'll get our function 1/8 x plus 3/16 x squared. So that's at the upper limit. Now, because these are polynomial terms that are not constant, evaluated at 0, that gives us 0. So minus 0, right? So this is the function now. This is the area function that gives me that area in green for whatever value of x I plug in. So it's like the integration is done. Now we have a function that we can just evaluate, right? But we're not quite done yet, because remember, the CDF, it says for all possible values of x. So we know what happens when x is greater than, when x is less than 0. There's a 0 probability because there's a 0 area here, right? There's an area of 0. Then we know if our x is between 0 and 2, then this function will give me the probability that my random variable is less than or equal to little x. But what if I plug a value of x that's bigger than 2? Well, once it's bigger than 2, then the PDF switches back to 0, right? So it would basically be it would be 0 here, and then I'd have to accumulate all the probability that's under the PDF, right? And then now over here, right? So it's basically, in fact, let me draw another scenario here, right? In fact, what I'm going to do is draw 3 to kind of illustrate the 3 pieces of this area function. So we got the 0, we got the 2. So let me do this, and then there's our piecewise function, and then there, linear function, right? So if we choose a value of x down here, there is 0 area, right? That's what this is saying. All right, so there's no area less than or equal to the x that I choose here. If I choose an x between 0 and 2, then I will get some positive area, right? And that's what this function will give me. If I now choose a value of x that's greater than or equal to 2, let's see what happens. So again, I'm sketching my PDF. It looks like this. There's our linear function, and then there's the other piece of it. So now if I pick an x over here, and I want to find the probability that x is less than or equal to this x, then it would be all the area up to and including this value of x. So it would be all of this now, right? And then 0 there, right? And that kind of gives you a picture of the whole idea of accumulating the area. If you start down here before any possible value of x, then yeah, 0 area. If you go somewhere within the interval of possibility, the realm of possibility, then you start to accumulate some positive probability. Then, if you go beyond that realm of possibility, if you now exceed all the possible values of x, then you'd have accumulated all the possible area. But for a PDF, that area is 1. So once you exceed the largest possible value of x, just as in the case of the discrete CDF, you accumulate all the possible area, which is 1. So whenever my x value is greater than or equal to 2, my area function is going to return a value of 1, right? So let's write that down, right? And so, in fact, let me do that. So actually, yeah, I can put the equal sign either. Let me do the equal sign here, and then let me do the equal sign here, consistent with how it was defined in the problem, right? So here is my sample space, and then once you go beyond your sample space, so when x is strictly greater than 2, right? Again, we would have accumulated all the possible probability, then my CDF would return a value of 1, right? So it will return a value of 1. Right? So let's put this all together in a nice piecewise form. Right? So in summary, right? Our C, why do I keep writing my X is so big? Must again be that level of excitement. So my CDF is piecewise. It is going to return a value of 0 whenever x is less than 0, because there's no chance there. There's 0 area associated with this interval. But then, when my x is greater than or equal to 0, but strictly, well, less than or equal to 2, then this function will accumulate the area for me, right? So this 1/8 and then 3/16 x squared. And then once I go beyond 2, I would have accumulated all the probability that's there, and then the CDF will return a value of 1. And this is for when x is greater than 2, right? So now this is the CDF function for the given PDF, right? Now, before I utilize this, I just want to remind you of some of the basic properties of the CDF that are still in play here, right? Because in a second I'm going to show you how you can use this to find your probabilities. But let me again sketch some functions, right? So if I sketch the PDF, you're probably tired of seeing this sketch, but this is what it is. 0, and then my linear function there, and then 0 again, right? So this is little f of x. Now let's sketch the CDF. Now, this is a quadratic function, right? This is a quadratic function. We have a basic idea of the shape of a quadratic, right? Again, I'm going to sketch it essentially over the real line, but the most important part of it will be, you know, when you're close to 0 and close to 2 and everything in between. So it's going to be 0 down here. Notice, even if I plug 0 into the middle piece, I will still get 0. So this tells me that this piecewise function is continuous at x equals 0. So there's no jump here, right? What it does, it starts accumulating the probability really nicely, really smoothly. So it starts here at 0. And then based on this is a quadratic. The leading coefficient is positive, so we know it's going to open up, right? So it's going to open up kind of like this. And then as soon as you get to 2, well, let's see, is there a jump at 2? Well, and from this side, it has a constant value of 1. If I plug 2 into the middle piece, I will have 1/4 plus 3/4, which is also equal to 1. So again, there is no jump. So I can actually put my 1 here on my vertical axis and say that as soon as we get to x equals 2, then the CDF would have accumulated all that probability, so it goes up to 1. And then after that, it's constant. So then after that, it's always 1, like that, right? So this is now the graph of big f of x, right? So, which is kind of interesting, even though my PDF is piecewise continuous, my CDF is continuous, right? In other words, this piece is continuous, this piece is continuous, this piece is continuous, but the PDF here has jump discontinuities. There are no jump discontinuities in this. And that's actually, again, a fundamental concept from calculus. And that's what the fundamental theorem of calculus says. It says that your area functions are always continuous, right? So really cool stuff. So I'll just make a note here to say that f of x has 2 jump discontinuities. So has 2 jump discontinuities, but big f of x has none. So it has no discontinuities. However, we do notice a problem, not really a problem, but something, again, that's an important concept from calculus. We do have a sharp corner right here. We do have a sharp corner. So even though it's a continuous function, it's not differentiable at that point, right? So it has no discontinuities, but is not differentiable, right, at that specific point. The part of the parabola is nice and differentiable, but at the same thing happens here. So it's not differentiable at x equals 0 and x equals 2, right? So it abruptly starts to accumulate the area, and then once it has accumulated all the area, then it abruptly stopped at the function value of 1, right? Okay. But when you look at it, we see all the same properties that we're used to, right? So I'll just list a few of them here. Is that So as x approaches negative infinity, the CDF approaches 0, right? So the limit as x approaches negative infinity of our CDF, that's always 0. And then similarly, as x approaches positive infinity, your CDF again approaches 1, just as we saw in the discrete case, right? These properties cannot be dependent on the type of random variable, discrete or continuous. We want to define these functions in such a way that the properties are exactly the same, right? Some properties might be in terms of summation, others might be in terms of integration, but we actually know that integration is basically infinite summation, right? So we have this. Third property, same idea. This function is non-decreasing. It never goes down, right? It might be constant, right, for certain values of x, but it never goes down because, again, it's always accumulating positive area. So f of x is non-decreasing. Come on. So non-decreasing, right? And even though I said at these, basically at the endpoints of the sample space, going from 0 to 2, the function is not differentiable. On the open interval 0 to 2, the function is differentiable because it's this nice parabola, right? And it turns out if I differentiate this, I get back my PDF, right? And that's our fourth property in that. So I'm not going to write it down as a piecewise function, but I'm just going to make this general note that for the values of x, that our CDF is differentiable. When I differentiate it, so if, for instance, if I take out the two endpoints here, the 0 and the 2, if I differentiate the parabola, I'm going to get back my linear PDF. So the general principle is that the derivative, right, of my CDF is my PDF, right? And again, I'm not going to really go too deep in terms of the points of non-differentiability, but basically, if I restrict it from if I only look at the open interval from 0 to 2, take out the sharp corners, then when I differentiate that parabola, I'm going to get back the line. And what will happen is, when I differentiate this constant part here, I'll get back 0. When I differentiate this constant part here, I'll get back 0. It's just at the endpoints where I have the weird jump, right? So again, I could say that this derivative, this relationship in terms of the derivative of my CDF is for all values of x except the two endpoints where you have the jumps, right? But here are the key properties for your CDF, right? Now, okay, so the properties are nice, but how can I use this, right? So let's kind of wrap this up. And what I'm going to do is I'm going to scroll on over here so I can have my PDF still on the, I'm sorry, CDF still on the screen. So basically, I guess this could actually be one of the properties. So I'll state it up here. So the fifth property is this. If I want to find the probability that my random variable, again, is in some interval, and I can include the endpoints or not, as we saw in the previous video. So let's say I have something like this. Then what I could do is I could find the area to the left of B, which would be this, And then I could subtract the area that's to the left of A. So again, take away the area that I don't want. If I want the area just to be between x equals A and x equals B, compute this, which will give me the area to the left of B, and then minus from that the area to the left of A. If you notice, what does this look like? This looks like your fundamental theorem, right? When you plug in the upper, plug in the lower, and take a difference, that's exactly what you do every time you evaluate a definite integral. But what we've done now is we've done the integration generally, so we can use this function at essentially what we've done is we've cut out the multiple integrals that you'd have to compute, and we just get to evaluate and take the difference, right? So just to kind of wrap this up with an example, so let's say, so here's an example illustrating how to use this fifth property. So for the one that we just computed, suppose I wanted to find the probability that x is between 1 and 1.5, right? There are two ways I could do it. I could go back to the PDF and actually do the integration all over again. Or, since my area function has already incorporated the integration, just use this property and take big F of 1.5 minus big F of 1, right? And now both of these x values are between 0 and 2, so I'm going to have to use the middle piece of my function. So if I plug 1/2 into my CDF, I am going to get this. So it's 1/8 times 1.5 plus 3/16 times 1.5 squared. We got that. And then I have to subtract 1 from this, so, or f of 1. So plug 1 again into my CDF. So we will have 1/8 times 1 plus 3/16 times 1 squared, right? And that's going to give me my probability. So all of this, so let's see, what do we have here? All right, so this is 3/2. So this is 3/16, and then plus 3/16. Now 3/2 squared is 9/4, and then minus 1/8, and then minus, because we got to distribute that negative there, 3/16. Right? So the 3/16 goes. Here we have 27/64, so 27/64 minus, and then write this as 8/64, and then 27 minus 8, that's 19/64. So that's the probability that this random variable is somewhere in the interval 1 to 1.5, right? So lots of ideas to really think about that we presented here today. Obviously the big one is the relationship between the PDF and the CDF. And then here in this last example, for instance, using the CDF to compute a probability, right? All right, I hope you found that interesting, and I will see you in the next video.